Good morning, everybody. This is Tony Verbsky. Gonna do a little trig. It might be evening, but anyway, Sunday morning for me. 9-7. It's the other four graphs. So we're gonna graph lecture, graph secant x, cosecant x, cotangent x, tangent x. Well, I already graphed them for you, but we're getting a little more detail now. So, sine and its buddy cosecant, 1, 2, 3, 4, sine. Now, deep down, I'm a radian guy, but I cheat in degrees all the time, so it's important to understand both. It makes it really hard to cheat if you don't like understand the realm that you generally cheat in. Anyway, 1, -1. Now, in math, 0 can be written as 0 over 1, and the reciprocal of 0 is D&E, undefined, does not exist. So this 0, this 0, this 0 become vertical asymptotes for sine's buddy cosecant. The reciprocal of 1 is 1. The reciprocal of -1 is -1. And this is 90. This is 30. Sine 30, 1/2. Reciprocal 1/2, 2. You see another one over here at 150. Bring it over. Right here, one tick in. This must be 210. 210, -1/2, therefore -2. 330. There we go. Approach the asymptotes. Do a better job than me. Here we go. Don't go over them. Whoa. Approach them. Approach them. Okay, so basically that's the graph. Now, the domain of CSC, cosecant x, is from -infinity to infinity, except we have problems at 0, pi, 2 pi, -pi, -2 pi, take away n pi. Where n, we don't write this, is in the integers, which for some reason is the capital Z in mathematics, where the integers are 0, plus or minus 1, plus or minus 2, da 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 da. So when you plug in a 0, it says 0 sucks. When you plug in a 1, it says pi sucks. When you plug in a -1, pi sucks. Plug in a 2, 2 pi sucks. -2 pi sucks. 3 pi, -3 pi. Basically, nobody writes this though. It's assumed that n is an integer. Anyway, range is kind of fun. Range is always easy. Just look at the graph. It's the y values. First y value is at -infinity, cruises up to -1, and hits -1. Then you got this no at 1. Yes, 1 to infinity. So it's -infinity all the way up to -1, inclusive, union 1, included, inclusive to infinity. Now we do the same thing all over for secant. Next page. Secant takes just a little more effort, not much. 2 pi, 1, -1. Cos, as you can see and know, looks like this. What I do is I add an extra tick, -90, pi over 2, and then I add another tick, 90 degrees, i.e. pi over 2 past 2 pi. 2 pi is 8 pi over 2, therefore 9 pi over 2. Not that anybody cares about that. Now, the zeros create vertical asymptotes. So the reason I extended it, man, that was bad. Oh, let's go with it. Reciprocal 1 is 1, reciprocal 1/2 is 2, 2, boom. You get the idea. Flip it over, flip it over. Perfect graph. Y equals secant x. Now, you're starting to pick up on this. From our previous graphing section, you learned that the period p nu was 2 pi over omega, and that's only true for sine, cosine, secant, sorry about reversing it there, cosecant, because they repeat every 2 pi, or 360 over omega, knowing that predominantly we work in radians. Our textbook goes back and forth, but in calculus you'll always be in radians. So because they repeat every 2 pi, that's why their formula is 2 pi over omega, where you already know. I'm going to graph cotangent first because I find that easier. 1, 2, 3, 4, drop in a vertical. But you got to remember the y-axis is a vertical. And you kind of do this. I wish I had a mnemonic device. Come up with one, I don't know. That'd be really cool, I guess. This has been working good for me, though. Blatant memorization. Pi, or 180. This is pi over 2. This is pi over 4. So if somebody asks you cotangent of pi over 4, you say 1. Somebody asks you cosine of pi over 2, you say 0. Somebody asks you cotangent of pi, you go undefined. Cotangent of 0, you say undefined. Now, see how this graph repeats every pi? I'm going to go back 2, 3, 4. See, I can throw another one in. The thing goes forever. But, you know, nobody likes, we could do this all day, actually. Anyway, this distance is pi. And that's the graph of cotangent. So you got to know it cold. You actually got to know it like right away cold, because we're going to be using it a ton here. Let's graph tangent and get out of the way. Tangent I don't like, because you got to go tick, tick, right, tick, tick, left. You got to drop in a vertical. You got to drop in a vertical. You got to draw something that kind of looks like x cubed. And this is truly 1, and this is truly minus 1. And you must approach your asymptotes. You know this distance is pi. And here's the hard part. Making this pi over 2, making this pi over 4. And then the graph goes forever. Now, I should have done the domain and range of the cotangent function, but while I'm here, the domain of tangent x is minus infinity to infinity. Take away. Okay. That here at pi over 2. Then where's the next badness? Pi away. So plus n pi. So if you go pi over 2 plus n pi, or plus pi, you catch the next one. Plug in a 2, 2 pi, you catch the next one. Pi over 2 minus pi, you catch this one right here. Now the range of tangent is awesome. It's double bar r, all real numbers. They don't let you use that in MML. Or minus infinity to infinity. It's the same for cotangent. So the domain is a little harder to write down. Let me go backtrack in my notes and talk about domain and range. All right. So go back to cotangent. The domain of cotangent is minus infinity to infinity. Take away all the verticals and pi. The range of cotangent is minus infinity all the way up to infinity. I say double bar r. Book says minus infinity to infinity. Let's go back. The domain of secant x is negative infinity to infinity. Take away, well, the first bad one's at pi over 2. And how often do they repeat? Well, the zeros of tangent actually repeat every pi, so the asymptotes repeat every n pi. The range secant minus infinity to -1 inclusive union 1 to infinity. I think I got them all now. All right, so back. Since is 2 dots high, 1 low. Since tangent and cotangent repeat every 180 or pi, p nu for those two only is pi over omega, or 180 over omega. But the v of x formula, where this is called the vertical scale, this is your trig function, and this is a parenthesis, doesn't matter, that's your known as your frequency that you're going to need in your p nu formula, x plus or minus b plus or minus c, where minus is right b, plus is left b, plus is up c, minus is down c. This formula still works. Actually, it works in just about all mathematics except for the frequency and any old function. Replace that with trig. In regular world, p nu is 1 over omega, not pi over omega, not 180 over omega. So in the regular function world, you just take the reciprocal of that, and that's basically, that's a compression factor. That's what the period does. The period, you're either compressing it or stretching it, and the frequency affects that. Frequency right now, in this case, for tangent and cotangent, is how many times it repeats every 180. For the other four, frequency is how many times does it repeat every 360. Well, anyway, let's get busy. Example. F of x, 3 secant 4x. The amplitude, you can't call it the amplitude anymore. The vertical scale is 3. Amplitude is only vocab for sine and cosine. Omega is 4. P nu for the 4 is 2 pi over 4, which is pi over 2. I'll go in radians. So what you do is you graph cosine. 1, 2, 3, 4, put a pi over 2. Graph cosine. Don't label it. With vertical scale 3. Flip it over, guys. Flip it over. Flip it over. Now, I don't always extend it, so let's go up the asymptote, down the asymptote, down the asymptote, up the asymptote, and if it bothers you, extend, finish it off. Done. Graphing and trig graphing is so much fun. Now don't worry, you gotta realize I just stretched it 3 units. It used to be way down there starting at 1, now it's starting at 3. I now have 4 oscillations or 4 cycles of the secant graph between 0 and 2 pi, because now it repeats every pi over 2, so I compressed the crap out of it horizontally, literally fit 4 of them in there. But as far as getting a base graph, that's how you start. MML is going to be a little more challenging. You can take what you have and then figure it out. But I always do this first. So let's do another. So y equals 3. How about a -3? secant, I don't know why I did secant, but 2x minus pi over 4 plus 6. Now, this is right pi over 4 up 6. I always pretend that I have like this little third grader can shift my points for me. So I'm never really that concerned about that. So I only see the rest of the problem, where the Vs is 3. It's a V flip because the negative on the 3. The omega is 2. Therefore, P nu is 2 pi over 2, which is pi. So now I got to graph secant, but that means I just got to graph cosine flipped. And I repeat every pi. This is pi over 2. This is pi over 4. This is negative 3. This is 3. And you ask yourself, do you feel like shifting it right pi over 4 up 6? Yes, I feel like shifting it right pi over 4. Yes, I feel like shifting it up 6. So, in red, you go 1 tick right, 2 ticks up. 1 tick right, 2 ticks up. 1 tick right, 2 ticks up. Get the pattern. Boom. Now you got to remember where your zeros were, because those are the new asymptotes. So the final graph looks like this. It's no fun shifting secant, cosecant, tangent, cotangent, left, right, up, down. It just drives us crazy. So I'm working all your homework, I'll suffer through it. That's the hard part. Everybody knows what the base function looks like. It's just when they go to shift it, you're like, oh, where did it go? So just understand that if you're graphing secant, use the cosine graph, actually shift it, but you got to remember where your zeros were. This, when I'm talking zeros, I mean, here, let's fill in the black. This 0 corresponds to this. This 0 corresponds to that. Because the zeros, that's where your asymptotes are. Well, here we go. Example. Y equals negative 3 tangent pi x minus 1/2 plus 5. The vertical scale, 3. There is a V flip because of the negative on the 3. The P nu is pi over pi, which is 1. Right 1/2 of 5. Right means negative of 5. But you don't look there, you don't do this till the very end. So you just graph, just cover up the 1/2 and the 5, you just graph that. So tangent flipped. 1, 2, 1, 2, throw in some vertical. Oh, let me undo that. Edit. Undo. Here we go. Throw in a vertical, throw in a vertical. This distance is now 1. Tangent upside down. Vertical flip. Tangent used to look like that. You have to vertical flip it. Hey, this is 1/2. No, it's not. This is 1/2. This is 1/4. this is now 3 and negative 3. Now you ask yourself, do you feel like shifting it? The answer is, I go right 1/2 all day long, but up 5? No, I don't want to go up 5 because I'm on a scale of 3. So if you want to go up 5, you got to actually now I can go up 5. That's the graph right there, except for the whole right 1/2 up 5. For you guys, I'll give it a shot. 1/2 is 2 ticks. So let me start here. 1, 2, up 3, 4, 5. 1, 2, up 5. 1, 2, up 3, 4, 5. Take the verticals and slide them over 2. Take this vertical, slide it over 2, and then your graph looks like that. See, the shift left, right, up, down is the hard part. And you just kind of lose track of where you went. So what I do, honestly, is, especially when I'm doing MML, and you guys are using predominantly only MML, so I hope you're still good graphers after this demo. But negative 3 tangent pi parenthesis x minus 0.5 parenthesis. Oh, I lied. I don't want to put this part. Delete. Parenthesis. I want to graph that first. Now, I know that you got to know everything I just did. Set your window nicely. So my window, my period is 1. So how about negative 1, 2, 1. Now I know what my ticks are. My ticks are 1/4. So how about 0.25? So I always know how to graph that piece. And negative 10 to 10, that'll work, I think. Mode, radians, okay with that graph. So the blue graph is my initial graph without shifting. So what I do now is I go y equals, it's kind of tricky. I take my last graph and I shift it right 1/2 up 5. So the trick is to get the y1 right here. So you go bars, y bars, function, y1, x minus 0.5 shifts it right 1/2 plus 5. So the red graph is my true graph, the one that MML better have written down. So here comes the section I actually drew in my notes. So, and then I shut this guy off and I look at my answer. So, then you're trying to compare screens, right? MML versus your screen. And what I do is I even look at the table because I know I'm going by quarters. So if you go to your table now, it's got like not set up right. So you gotta go second table set. And I don't care if it's -1 to 1, -2 to 2, it doesn't matter, the graph. But, second table set. Start at 0 is fine. Change in table 0.25. Now it should be a little better. So there's a vertical asymptote at 0, at 1, at 2. So you know where all your vertical asymptotes are, so you check MML, make sure that's where the vertical asymptotes are. And then you can actually just look for the 0.55 and make sure it lines up. You better have a 0.5, 1/2 5. If you don't, that answer is not right. Anyway, best to do it by hand correctly, but calculator, valuable weapon, very important. You learn how to use it. Well, you're stuck with the right guy. I use it all the time. All right, I'm going to take a look to see where I am. I know I pretty much got this, but there's some stuff that I keep forgetting to say, so I'm going to make sure I get it in this because I'm only at 25 minutes. I should probably do a cotangent graph just for kicks. I'm going to look at the problems. Here's a tough one, problem 65. Section 9.7, page 707. It's going to be cotangent. It's not a proper form. This 3 needs to be out here. By the way, the A value is 1. It's implying you must shift in radians because there's no degree symbol there, so we're working in radians. I was going to work in radians anyway. Anyway, the 3's got to come out. You know, like, wait a minute, there's no 3 here, so put 3 over 3 in there. Now you rewrite it, 3 x plus, you took that 3 out, pi over 12. So that's left pi over 12 of vertical scale of 1. No negative, so don't flip it. Frequency is 3. Visits its period, old period is original period, which is pi. Visits it 3 times, so this is compression. P nu, use the formula pi over omega, so it's pi over 3. So if I were to graph this, 1, 2, 3, 4, throw in a vertical, memorize the graph of cotangent to be this, with 1, negative 1, P nu is pi over 3, making this pi over 3, making this pi over 6, making this pi over 12. Left, pi over 12. We're about to destroy our paper. We're going to move the asymptotes 1 tick to the left. We're going to move the 3 points 1 tick to our left. So, move the asymptote 1 tick to your left. Move this asymptote 1 tick to the left. Move this point 1 tick left. Move this point 1 tick left. Move this point 1 tick left. And let's finish it off in green. I don't like shifting it. I just like to say, oh, I see it, and then I move to the next problem. I'm looking through all your problems in your reading now. It looks like they're working you over quite a bit on some, you know, that thing where you got to pull a number out. So let's do another one, I guess. 46. Y equals 2 plus 1/4 secant 1/2 x minus pi. I hate it when they put the up to in front. This is still the vertical scale. It just kind of squashed the cosine graph big time. This is not proper format. I need to pull a 2 out down low, so I put a 2 over 2 in, and now I can write it appropriately. So ripped out the 1/2, rip out a 1/2 minus 2 pi. So the vertical scale, 1/4. No vertical flip, omega, 1/2. P nu for the 4, sine, cosine, secant, cosecant is 2 pi over 1/2. You get used to calling this 4 pi in a heartbeat. You reverse copy dot flop, not reverse copy dot flop, just copy dot flop. Flip over the 1/2. Then you go right 2 pi. Well, initially I don't feel like going right 2 pi or up 2 right here. But I will graph a basic secant graph with period 4 pi. So here we go. Secant looks like cosine. So you graph cosine. You go 1, 2, 3, 4, cosine. The new period is 4 pi. Vertical scale 1/4. Now, do we feel like shifting this graph right 2 pi? Yes. 2 ticks. Do we feel like going up 2? No, I don't. Because that's going to shoot my graph all the way up here. 1/2, 3/4, 1, 1.25, 1.5, 1.75, 2. And I got to move every point up, so up 2. So I got to go 2 1/4 up. So I got another tick beyond that. So I refuse to shift. Can you do that in MML? No, but we can do this in our regular problems. Okay, so the zeros are the asymptotes, and then you just flip it. Oh, better use a different color. Flip it over, approaching the asymptotes, and then you just tell the grader, me, you go, I'm going to go right 2 pi, which, hey buddy, is that direction, and I'm going to go up 2. We're all smart enough to see where it ends up. But what happens if it's MML? This, you need to know this much for sure to be a good cheater in MML if you're going to use your calculator. This might be good enough to answer the question in MML, but when somebody gives me this takes a little bit more skill. Let's see if I got this down. Seems like I had problems in the previous year. Okay, so what we want to graph basically is 0.25 cosine of 0.5 parenthesis x minus 2. Still want to do that. Once again, when I cheat, I do exactly what I do on my paper. Now, it's important to get a good window set. And you're going to set your window from 0 to 4 pi. Your scale, you might as well go by pi's. And initially, you want to go like negative, because you're negative 0.5 to 0.5. And maybe, I don't care about your y ticks, let's go 0.25. Let's see if we got the graph. Yeah. So that's a good graph of cosine right there. Now let's see if we can do the reciprocal of that graph and get what we need to do, because we know what it looks like. This is the first time I'm probably trying this in my life, so give me a second. If this doesn't work, you can't be mad. If it doesn't work, it's brilliant. Reciprocal meaning x to the minus 1 key, I want to take the reciprocal of y1. So vars, y vars, function y1, reciprocal. Let's see if it flips it over. Come on, come on. I think we got issues. I'm going to do zoom 0, see where it ended up. It definitely didn't end up where it's supposed to be. Zoom 0. Okay, not good. Oh, not good again. All right, let's do this. Let's do it right then. Clear, clear. I'll work on that tonight. Just think I can get it to work. So if you want to graph secant, first of all, you got to go. Let's get this piece here. So let's just graph secant of 1/2 x. That's what I'm going for. So 1 divided by secant, which is cos 0.5 x. That's a good start. So let's graph that. Graph. Uh-oh. Are we in the wrong mode? One divided by cosine 0.5 x. Zoom. When in doubt, 7. There we go. I think I have my window messed up, guys. That last one probably would have worked too. Okay, so anyway, that's what I'm supposed to have. Now, I'm going to keep going with the thing that didn't work. I go 0.25 vars, y vars function, y1, and it should squash it down. Yep. Now let's shift it to the right. This turned out to be a pretty good example. So you take the last graph and you shift it to the right. So you go vars, y vars, function, y2, and shift it to the right to pi. So there's the function shifted to the right to pi. And now all you have to do is go up 2. I think I'm always going to teach it this way now. Vars, y vars, function, and y3, and go up 2. Zoom trig. I think zoom trig will get them all. Maybe not. So you might have to adjust your window manually to get that on there. Man, I'm hitting my 38-minute mark. You know what I'm going to do? I'm going to do an extra, summary lecture for the whole chapter. Might even do a couple, like extra graphs, bonus lecture, so I can actually get more of this in. Because I really, really personally want to develop some really good MML skill. Because I'm learning a ton teaching it like this. And there we finally go. They shifted it up to. Their scale was pretty good. So if you do it shift by stretch by shift by stretch, it's a pretty good way to get it done. Now granted, I have the color graphing calculator. If you don't have a color graphing calculator, this becomes a train wreck. So you got to learn to turn them on and off. So I think I want to do more of that for sure. So I'm going to end this lecture knowing that I'm going to come in with a bonus graphing lecture. See you later.